Hi to all. My name is Jasmin Hadzajlic and I'm coming from a company named Microwee, and today I will talk a bit about acoustic echo cancellation in embedded systems. Actually, I will first get some brief about echo, about general echo cancellation idea, and then I will most of the presentation is speaking about the problem that we had on our on our project. Yeah. So let's start. So I put here some acoustic echo definitions. So echo is actually a reflected signal that we get on the source, and acoustic echo is audio signal that we get back to the source of it. So, for example, we have echo in meetings, in conferences. That's the first picture. In the near-end room, we have one speaker, which is loudspeaker, as we have right now, and also we have a microphone or microphones, or more of them, and we are speaking to someone else in another room, and that person also have the same setup. And when we are speaking to that person, some of that sound from the other participant or far-end room gets rebound of the room and also gets directly passed to the microphone and gets back to us, and then we hear our voice on our end. And that's echo, and that's something we want to cancel because it's not nice to have. The problem that actually we have is like chatbot device, and that's the other picture where chatbot device is speaking through the speaker and listening to the microphone. And in the need when we want to make it speak and also listen at the same time, device hear itself. So that's the problem. And also what is worth to mention is that this acoustic echo, as many things in nature, can be modeled as low-pass filter. In ideal case, it is linear, but of course, nothing is ideal. So it's non-linear, but we'll see. So, sorry. Okay. So, how do we do echo cancellation? So I said that a room can be modeled as a nonlinear filter, and we are trying to make the same filter on our side. That's here adaptive filter, and then we have reference input. That's a reference signal that we pass to the speaker. And we pass that through the adaptive filter, and then that gets subtracted from the microphone. So in the room, we have a real-world filter, and here we are trying to adapt our filter to match that, and then as the output of this sum, we want to have only clean signal, which is our voice. So we are speaking to the device. That's general idea about echo cancellation. Of course, because it's not linear, it's non-linear, we try to, there are like different solutions here to have like non-linear filters, but the easiest one that we put on the presentation is actually finite impulse response linear filter. And it works good if everything is okay, of course. And the rest of echo could be cancelled by additional processing, which is this residual echo suppression. And after that, we can add some more noise reduction. And now to the problem. So I already mentioned that we have kind of chatbot device. That device is not meant to be chatbot device, so it doesn't designed to be used like to speak with it, to get some response from it, but for some other features. But as we have like speakers and microphones in it, why not do that? And we already had implemented the speech-to-text recognition and we hear what a person is saying, and also we have text-to-speech, which is what device is telling us. But when we wanted to use something called continuous speech recognition, which is to speak both, so both device and us are speaking at the same time, we got this problem. That small device and microphones and speakers are near each other, so that also make echo more powerful. Yeah, and also because we are using Linux on the device, we are using Pulse Audio and as a reference channel, so as an input, we added like a virtual channel, which we used as a input for acoustic echo cancellation. Acoustic echo cancellation is not what we implemented. We were using acoustic echo cancellation from Microsoft Speech SDK because we were already using Microsoft Speech SDK for text-to-speech and speech-to-text, and we used their acoustic echo. But as I said, when we started using continuous speech recognition, we got the problem with echo, and there we realized that acoustic echo is not working properly. Then we started detecting our problem. Our first step was to ask Microsoft what is wrong, because it's not us, it's them. And we tried to approach on their support page, and the response we got is use headphones, don't use loudspeakers, which is not good for us. So after we detected the problem, we wanted to try to record some data on the device and then copy that to the desktop machine and then try to process it. First, we tried several one GitHub repository with several adaptive filters to cancel echo, but that didn't work. Actually, the only one which gave us some result was Kalman adaptive filter. But for example, for audio record with length around 1 minute, it took around 15 minutes on desktop machine to process it. So it wasn't useful in real time. What we also tried using one educational kit with DSP processor to test it, because it also had already implemented adaptive FIR filter, which was working for noise reduction, but that also didn't help us for some reason. Then after we tried all these solutions, we started to detecting more problems on our hardware. So what we did, we recorded system response identification by playing sine wave sound on the speaker and then record it to the microphone. We did that for a lot of frequencies. On all these graphs, there are on the x-axis are frequencies as shown, and we played a lot of sine waves, for example, from 50 hertz to 8 kilohertz every 50 hertz step or so, and then we recorded amplitude response and also phase response. Based on that, we did inverse Fourier transformation to get that actual filter, which should be in ideal case, or at least it should give us some results. That should be actual room filter. So we tried to do it like hard-coded, instead using adaptive filtering. When we did that and put that filter instead of adaptive filter in the schematics before, we didn't get any results. Echo was still there. Then we started to analyze actual response for sine wave frequencies, and there we saw that when we play for example, 400 hertz frequency on speaker. On microphone, we get higher harmonics, which are with significant power. And that is this picture here. So we are playing 400 hertz sine on the speaker, and this is audio or Fourier transform on from microphone. And here you see we have 400 hertz, but also 800, 1200, and so on, all higher frequencies. And the difference between bass harmonic and third harmonic is around 20 decibels, which is not good at all. Then we wanted to detect what is the problem. Is it the speaker or microphone who is giving us this higher harmonics? Then we used speaker, play sine wave on it, use desktop machine to record it because we were sure that desktop is working fine. Then we saw that on the speaker we get higher harmonics, but to be sure we also played some sound on desktop, recorded it on the device, and there we got no higher harmonics, so microphone was fine. So the problem was speaker. Then we disassembled the device and saw that we are using speaker with 2 watt power, and we are using amplifier with 3 watt, which is not good. And also beside that, amplifier was configured to use more than 3 watt power. So we were driving speaker with more power than its nominal power, and because of that we got higher harmonics. And we disassembled that speaker, added 3 watt speaker, and then we got no higher harmonics, and we got better acoustic echo cancellation. On the third picture, there is total harmonic distortion per frequencies on our setup, and as you see, especially on lower frequencies, we have really high harmonic distortion. And on lower frequencies, of course, there is human voice and also voice of the device because it's talking as human, and that's also a big problem. Maybe in case where we were playing some other sounds, we could cancel that, but we couldn't cancel actual speech. Also, it's worth to mention that different oscillators using for microphone and speaker sampling could be a big problem because none of oscillators can be exactly the same, so sample times are not exact and they can drift over time, and that could also make a lot of trouble for echo cancellation. And then I can move to some conclusion or advices if anyone want to take some work on acoustic echo cancellation before designing device, before designing hardware, audio hardware. Everyone should think about what it is used for. And as you saw in our case, that was the actual problem. We were using wrong speaker and amplifier pair. Also, yeah, that's the second also point. Also, I forgot to mention that we also try to use a WebRTC plugin for Pulse Audio, which is software way to do echo cancellation. In that, WebRTC is really in use everywhere, but it didn't give us, actually it did give us some results. We didn't have echo, but we also didn't have our voice. So it was too aggressive for our case. So we couldn't even hear our voice, and it didn't make much sense to use it. And also that by using WebRTC, Pulse Audio CPU usage went, I don't know, to about 80% or 100%, or that's like 1 of 4 cores on our processor, and that's too much processing power doing something that's not main thing. So also do as much processing as you can on hardware, either using DSP, some specific FPGA, or sound card with integrated acoustic echo cancellation. Also, while doing this task, we were researching another alternatives, and some some out there advices to use more microphones and do beamforming, and by that you can cancel sound from specific direction. For example, you have one speaker and 3-4 microphones, and then you can detect from which direction is that speaker playing and cancel only that, but hear everyone else in the room. Also, as Microsoft suggested, use headphones or increase distance between speakers and microphones to make echo lower. And there are also directional microphone speakers which are doing directions. And what also want to mention it that this room also has these acoustic panels which are absorbing some sounds, so it's even better results with that. And as last slide, I want to just mention where is echo cancellation where it is used. This topic is like, I don't know, from 1950s, so it's really old, but it's still a really hot topic. And Microsoft made acoustic echo cancellation challenge last year for conference on signal processing, on acoustic signal processing, something like that. And they provided data sets, so anyone who wants can do some processing on that and make either software or hardware implementation of it. We found one GitHub repository which was doing this using neural networks, but that worked without harmonic distortion, but on harmonic distortion it didn't work, of course, because there was too much nonlinearities. Besides that, there are well-known meeting applications, Teams, Slack, Meet, Zoom, Skype, so on. All of them are using echo cancellation and noise cancellation. I wanted to try to cancel echo on this application, but there is only button to disable noise cancellation, so I haven't tried it. And also, as in hardware implementation, there are a lot of conference speakers which are using loudspeaker and microphones, and that works really good in all conference rooms, which means that they are using some quality hardware. What we also found that there is a specific acoustic echo cancellation card which doesn't offer speakers or microphone, but it offers channels, input channels and output channels, where you can plug in a reference channel, microphone, speaker, so on, and that card as the output give us echo-free sound. And what else we found, that there are a lot of DSP processors which has with already implemented stuff on them. One of those is Analog Devices ADAU 1467 evaluation kit, and Analog Devices even offer algorithm with license for echo cancelling. This video on this topic can be found also on YouTube. It's really interesting. And that's it from my side.
I'm not even gonna look at the slider anymore. Do you have any questions regarding the, yes?
Okay, yeah. So you eventually reverted from the adaptive filter to non-adaptive, right? Then was that the final call?
No, the final call, we're still waiting to a response for a client actually, but the final call is to switch speaker with correct one, because we were using 2-watt speaker. And
but what about filter? I understand you're going to fix
we will
upgrade hardware.
Yeah, we will stick with Microsoft acoustic echo cancellation.
Oh.
We will stick to that until they say.
Yeah. So my question was, never mind what your choice is. If you had a non-adaptive filter, you needed to have some kind of calibration.
Yeah, of course.
You have to do it.
Yeah, of course.
So there will be like a button or something, that an instruction to user, please calibrate once.
Yeah, of course. Yeah, of course, but this was actually why we did that non-adaptive filter, is just to try to check what is an issue. and we tried several echo cancellers. None of them worked. Okay, let's try to actually get filter response of a room and get that. So only in a specific condition. Yeah.
That's fine.
Yeah, but of
If
course.
you stick with that, you needed to do a calibration for each individual room.
Yeah, and colleagues remembers that we played sine waves, which is really not nice to hear. We go out of the room, let it like for 1 hour to go over all frequencies and to get the response. So I'm not sure in real usage. I don't think that's. Yeah, of course. or they buy it once and then jump through the window. Thank you.
Further questions? Orson, right?
I have one question and one comment. So, question, anyone to know, maybe Amazon had the same problem and then they named their home assistant because of that, like Amazon Echo?
To be honest, I haven't used them, but do you know if I use, for example, Google, and you need to say, okay, Google, say something, and then when Google is speaking, you cannot interrupt it. I don't know if that's the case for Amazon and you can interrupt it. Yeah. In their case, they used good quality speakers, so they can do normal. Yeah.
Another thing, actually, you listed a couple of big companies that they actually did there. But also we have one company in Bosnia, it's Vital Systems, so I actually worked there. So they also did like these conference calls and everything they are still doing. So you can, I can help you with that. You can actually check how they solved it. Their solution is heavily based on WebRTC, but you can still check because they did some additional stuff. So you can actually check.
Thank you, that would be good. Yes, sir.
Anyone else?
Okay, thank you.